afternoon is Professor Li-Hung Wang. And many of you know him from his very famous book on the biomedical optics. I was reading it on my flight here, in fact, trying to make sure I can combine traditional imaging and traditional photography in interesting ways. And of course, Dr. Wang is the inventor of the functional acoustic tomography. He recently received the award of the 2010 Joseph Goodman Book Writing Award for his book on biomedical optics, and he just told me that he also received the Mies Medal given by OSA, which is a high honor.
Thank you. Thank you, Ramesh. Let me thank the conference organizers for inviting me. Is the game too high, or I think there's feedback? Again, thanks to the conference organizers for the kind invitation. It's my first time to come into this conference. So today I'll be talking about photoacoustic tomography. Our goal is very simple. We want to break through the optical diffusion limit for super depth imaging, and we do it using ultrasound. Washington University requires me to disclose my financial interests with two companies, Microphotoacoustics and Endra, which are commercializing photoacoustic tomography. We're funded by NIH. Starting from the motivation and challenges in this field in general, I'll be talking about two major incarnations of photoacoustic tomography, namely photoacoustic CT and photoacoustic microscopy. And in the end, I'll close with a discussion and summary. The very first question is, why optics? Optical imaging is very unique in terms of the contrast it can provide. First of all, it's very safe to use light because it's non-ionizing radiation, very much unlike X-ray photons where you deal with thousands of EVs. In optical regime, you deal with only a couple of EVs. So light is non-carcinogenic. From a very fundamental perspective, among the entire optical, in the entire electromagnetic spectrum, light is the only region that allows you to probe molecular structure directly. And so we can measure molecules and tissue compositions directly using light. From the optics perspective, we talk about various contrast mechanisms, absorption, scattering, fluorescence, and whatnot. Today I'll focus on optic absorption, which probes a number of biomolecules: oxyhemoglobin, deoxyhemoglobin, melanin, lipid, water, even DNA and RNA. Now, by using the endogenous contrast that's intrinsic in the tissue already, we can provide you functional imaging of a number of parameters, such as the concentration of hemoglobin and the oxygen saturation of hemoglobin, which are important hallmarks of cancer. You can even image cell nuclei. Or blood flow by using the photoacoustic Doppler effect or optical Doppler effect. Biologically speaking, if we introduce exogenous contrast, we can provide you molecular imaging of all sorts of biomarkers and even reporter genes, so we can track gene activities. So where's the challenge? There are two very fundamental challenges in high-resolution optical imaging: diffraction and diffusion. Diffraction as a wave phenomenon limits the spatial resolution of all ballistic imaging modalities: conventional wide field, confocal, two-photon, and optical coherence tomography. They're all subject to the same limitation. However, you can overcome the diffraction limit and achieve what's called super-resolution imaging. Diffusion as a scattering phenomenon limits the penetration of all ballistic imaging modalities to about 1 millimeter in the skin. We want to find a way to overcome the diffusion limit. Photoacoustic tomography is one method for that purpose. This movie shows how photons propagate in biological tissue. And you can launch a collimated photon pulse into a piece of tissue. In the beginning, photons travel together as a group, That's the so-called early ballistic regime. But the photon propagation transitions from the ballistic regime into the later diffusive regime within a matter of a millimeter or so in the skin. And that depth is the transport mean-free path. And that's the mean-free path between equivalent isotropic scattering events. That's extremely short, translates into about a millimeter. The physical scattering mean-free path is about 0.1 millimeters, 100 microns. And you can see that presents a huge challenge in biological tissue for high-resolution imaging, because scattering is a chaotic process that's going to kill your resolution. And we're going to focus on the diffusion problem today. From the imaging perspective, if you simply project a collimated laser beam or even conventional beam through a piece of tissue, both the illumination photon path and the detection photon path will be tortuous. As a result, if you want to capture a shadow of the middle plane structure, it won't give you a shadow. This is very different from X-ray projection imaging, where you're dealing with a single scattering regime. However, if you can slice open the tissue to expose the middle plane, you can form a very good image because the detection photon path now is clear. To get a good image, you only need one-sided clarity, excitation or detection. So here, obviously, we're focusing on the detection side. This is obviously invasive, it's not useful for imaging. A little better approach is to optically clear the scattering on only one side of the tissue. Now you have a well-defined detection photon path, which allows you to form a good image as well. But this optical clearing process requires the use of toxic chemicals, so it's a toxic process. A much better idea is to convert light into sound, because acoustic scattering is about 1,000 times weaker than optical scattering. By detecting the ultrasonic waves, we can form a very clear image. So we're doing the equivalent of case B or case C, except without invasiveness or toxicity. Right. Now, even though we're listening to the sound coming out of tissue, our contrast is optical. So we're combining optical contrast and ultrasonic resolution in deep tissue imaging in a single modality. We're essentially listening to optical structure as opposed to look at it. Photoacoustic tomography obviously is based on the phenomenon of photoacoustics as a physical phenomenon. Photoacoustics was first reported by Alexander Graham Bell over 100 years ago. He had this concept of photophone instead of telephone. He wanted to encode sound into a light beam, then transmit the light beam in space, and convert light back into sound again through the photoacoustic effect. This might be the first optical communication device. Nowadays, we obviously use optical fibers instead of free space communication. And you can see the limitation here. It requires line of sight propagation. So this concept really never took off. So what we're interested in is the photoacoustic effect taking place right here. When light is absorbed by the absorber, it generates a temperature rise. Because of thermoelastic expansion, it'll generate acoustic emission. Nowadays, we're interested in the ultrasonic regime instead of an audible frequency regime, because the ultrasound frequency will be higher, the wavelength will be shorter. As a result, you get better resolution. Now, of course, Bell will be surprised today that we're using his phenomenon for tomography, and tomography was not even in the lexicon over 100 years ago, of course. So let me start with the circular geometry for photoacoustic computed tomography. We expand the laser beam, typically nanosecond impulse width. Make sure we stick with the safety standards. You never want to drill a hole when you try to image something. So the laser fluence has to be small enough. The key difference between ballistic optical imaging and our method is we allow photons to scatter. Excuse me. Because that's the only way to penetrate deep into biological tissue. Any photons are useful photons because as long as light is absorbed, it'll be converted at least partially into heating. For every millidegree temperature rise, through the photoacoustic effect, we can produce 8 millibars pressure rise, which is already above the noise level for our photoacoustic ultrasound detectors. Now, by detecting the ultrasound emission outside the tissue, we can form a very good image. So this is a mathematical problem. It involves reconstruction. Again, because ultrasound scattering is so weak, we can pinpoint the optical absorption sites with various strengths and form a map, which is our image. Let me start with the simplest analogy I can think of, a thunderbolt. If you want to pinpoint a thunderbolt, when you see the lightning, you get your time 0. When you hear the thunder, you record a time delay t1. Since we know the speed of sound, we multiply the speed by the time delay. We define a radius for a spherical shell on which lightning took place. If you have 3 such measurements centered at different locations, you can triangulate and pinpoint the thunderbolt. So photoacoustic tomography in the simplest scenario is essentially triangulation based on the photoacoustic waves. Except we deal with a 3D heterogeneous object as opposed to a single point source. So let's say start with a 3D object. We bathe the object with optical photons, generate a 3D complex photoacoustic source distribution. Then the best we can do is to place a lot of ultrasound transducers outside the tissue. For a typical ultrasound detector, at time t, after your nanosecond laser pulse, you integrate the initial pressure on the spherical shell, because ultrasound takes time to propagate. And that spherical integration is called spherical radon transform. I'm sure you've heard of the linear radon transform in X-ray CT, where you integrate the X-ray attenuation coefficient along the X-ray propagation direction. Here we have to spherically integrate the pressure waves on a spherical shell. So it's a 2D integration versus a 1D, and it's on a curved surface instead of a straight line. Radon never inverted this problem. Very likely a few years ago we found a universal back projection algorithm that works for 3 standard detection geometries: planar, cylindrical, and spherical. P is the pressure we detect at detector position R0, and that goes around its detection surface. Every detector gets a time trace, so P is a function of time t as well. And you have to properly time delay the signal when you back project it into the object. So that's why you have this time delay term. And then omega is your full detection aperture. So you want to integrate all your detector signal properly over the full aperture. If you use the pressure only, you will get a pretty good approximation already to the initial pressure induced by the laser pulse. But if you include this time derivative of the pressure, which is really the high frequency component, you're basically biased toward the high frequency components. It's a filtering process. And the combination of the 2 terms will give you an exact solution. And that will produce this initial pressure P naught induced by the laser pulse. At first glance, this is a mechanical property, not an optical property. However, the magnitude of P naught is proportional to the amount of energy deposition per volume. And so that reflects optical absorption. As a result, you can measure optical contrast through the reconstruction of the initial pressure. This is the first functional photoacoustic image, which was acquired in a small animal. We wiggle the whiskers of a small animal. The contralateral side of the brain was activated hemodynamically, as shown in red here. And so the grayscale reflects the structural image of the cortical blood vessels. So light was able to go through the scalp and skull and reach the brain cortex and still come out with good images by using photoacoustic tomography. So this work really galvanized the field and initiated exponential growth. You can see since '03, the size of the field doubled every 3 years. And since 2009, the conference on this topic became the largest in Photonics West, which is the largest gathering in biomedical optics. And this year, in 2011, we were the largest by far. A very natural question: why is photoacoustic tomography so exciting? Among all imaging modalities, photoacoustic tomography is the only functional and molecular imaging modality that allows you to image at multiple length scales, covering organelles, cells, tissues, and even organs. And I'm plotting the penetration capability versus the spatial resolution here. Every bar in this chart is a realized real system, actually experimental system that's working in our labs. So forget about the acronyms. I'll come back to some of them later on. And why is this so important? In current practice, for microscopic level imaging of organelles and cells, we use optical microscopy. For macroscopic imaging of tissue and organs, we use non-optical imaging. We use MRI, ultrasound, CT, and whatnot. So we're talking about different contrast mechanisms. They are so different, you cannot even correlate images acquired at different length scales. By using photoacoustic tomography, we can bridge that gap. It allows you to correlate images. Excuse me. My hope is that photoacoustic tomography will enable systems biology research at multiple length scales and accelerate translation of microscopic lab discoveries to macroscopic clinical practice. This is a ring array-based system. So this ring here represents 512 elements of ultrasound transducers. And we have 64 channels of A2D with 8 laser shots. We can acquire a 2D image, which takes about a couple of seconds. And we actually started our image using a single element that would take about 20 minutes to rotate around the object. And so this system is a lot faster than the first generation. And this is a representative image acquired using the system. And again, you can see the brain cortex very well. You can see the blood vessel structure in the brain. And this is what you see with the naked eye. And you can see the skin, that's it. The scattering kills everything. And this is very much like the early talk about underwater imaging, except this is a lot, orders of magnitude tougher because of scattering so strong. Infrared path, remember, is 100 microns, 50 microns to 100 microns, the width of our hair. Where ocean water, remember the number cited is about 5 to 10 meters. If you remove the scalp, and this is what you see with the naked eye, you can see the brain cortical blood vessel structure quite well. You compare this invasive photograph to this non-invasive photoacoustic image. You can see how well we can recover the structures hidden below the skin. And this is very recent data we acquired by imaging a small animal full body. We're scanning along the trunk of a small animal, and you can see how well we can delineate some of the internal organs. Right? It's laid out here in this still shot: kidney, vena cava, GI tract, colon. Right? So this is getting very exciting because it has been a challenge to image a whole body, even for a small animal. And this has potential implications in drug discovery down the road. We're always thinking about imaging bigger animals, even eventually human brain, even though we started from small animals. So we're imaging rhesus monkey heads. And very luckily, I would say, in this case, even by avoiding correcting the wavefront distortion due to the skull, we can get a reasonably good image to begin with. And you can obviously see some distortions due to the skull. but we've got sufficient signal-to-noise ratio to work with. That's always the most important aspect from engineering perspective. And if you remove the skull, you take a photograph, you can see some of the structures here. You can compare the two, right? See how well we can recover the structures. And obviously, we're moving toward human imaging where the skull can be even thicker. We understand the challenges because for human skull, the thick skull is going to distort the wavefront so badly you have to correct it. We have active NIH grant to pursue that direction. And in this case, very different from pulse-echo ultrasound imaging where your ultrasound has to propagate both ways. In our case, the ultrasound signal just have to propagate one way out. And so the distortion is smaller and the signal attenuation is weaker as well. And I still have high hope on that problem. Photoacoustic CT also comes in a linear geometry. It's highly scalable, right? This is very simple. Let's just focus on the bottom line. So if you look at the lateral resolution and axial resolution, they both are inversely proportional to the ultrasound frequency used. But the penetration capabilities are also inversely proportional. If you take the ratio, right, between the penetration limit and axial resolution, you get roughly a constant. Very likely that constant is about 200. So that means you have 200 pixels in the depth direction to work with. And whenever you get more than 100 pixels, you get a decent image to work with. So what we're looking at is the scalability afforded by ultrasound. And we're scaling to a clinical ultrasound machine here. This is a ultrasound machine made by Philips, and this is a joint project with Philips. We've adapted a standard clinical ultrasound probe. It's a linear probe for photoacoustic imaging without giving up on the ultrasound imaging capability. So this is for simultaneous ultrasound and photoacoustic tomography. The ultrasound probe is flanked with two fiber bundles. And with a single laser shot, you can capture all 128 channels worth of data. And so that gives you a B-scan 2D image. And intrinsically, you can see that photoacoustic tomography is a very rapid technology in terms of data acquisition. We're targeting a few applications. One is reporter gene imaging at depth. And you might have heard of green fluorescence protein imaging, GFP imaging, which is based on fluorescence. To get high-resolution images, you can only penetrate about a few millimeters into biological tissue. So here, even at a depth of 5 centimeters, we can still get sub-millimeter resolution. So this cannot be achieved using standard fluorescence technologies. We're also targeting breast cancer staging. Right now, the standard procedure is a surgical procedure. You have to identify the central lymph node using radioactive materials. Then you cut open the breast, follow the dye that was accumulated by the first draining node, the central lymph node. Then take out the central lymph node, do histology. 80% of the patients who go through the procedure turned out to be benign. So the entire outcome of that surgical procedure is just to identify there's no metastasis on this patient. The news is good, but there is complications associated with that surgery, not to mention the expenses. So we want to convert that into a needle biopsy procedure. And we started an animal study. There's a small animal here. We increased the depth of penetration by adding additional tissue outside the animal. And you can see this central lymph node right here, if I can replay the movie. Our next goal is to insert a needle. And we use photoacoustic tomography to guide the needle here as well. And the needle can be inserted toward the central lymph node to take out some tissue. And then you can do a histology. The contrast is about 8:1. If you look at the ultrasound counterpart of the same needle, it's right here, but it's really hard to make out until you start poking, right? So this contrast is only 1.2:1. Right? You can see the huge difference here. A very important question for optical imaging any time is the penetration capability. Even though we're using multiple scattered photons, it'll still attenuate. So in our lab, we demonstrated in an ex vivo study that we can penetrate about 7 centimeters. Right? So this is very exciting. Of course, the ultimate answer has to come from in vivo studies. So in the next 3 slides, I'm going to show you some unpublished data in collaboration with Philips. This is very recent data, but it's very exciting. So this is our first patient studying in a human breast cancer patient for a sentinel lymph node biopsy. And this image was acquired before the injection of the methylene blue dye. And this dye is currently clinically used for standard procedures. So we're not introducing any new chemicals into our study. And what's encouraging is that even at a depth of 6 centimeters, you can still identify certain features. And this is really not the main purpose of this particular study, because here we want to see the sentinel lymph node. And using the methylene blue dye only, without injecting any radionuclides, right? The standard procedure involves radioactivity. We don't. We can see the sentinel lymph node with a huge contrast, with a more than 6:1 contrast between the node and the background signal. And obviously, it is just the beginning. The later studies is going to involve needle biopsies of the sentinel lymph node. And this is a comparison at 18 minutes and 22 minutes post-injection of methylene blue dye. You can see at early times, you can still see the dye flowing in the lymph vessels. But if you wait long enough, they'll accumulate at the sentinel lymph nodes. Right? That's like one stop all the dye molecules will make. And you can see that as a beacon, as bright as a beacon. Right. Let me talk about photoacoustic microscopy as well. Remember that map I showed, and one advantage of our technique is to cover the entire lens spectrum. Photoacoustic microscopy is targeting, obviously, microscopic level resolution, but still, to begin with, a few millimeters deep. Right? We want to break through that 1 millimeter diffusion limit. In the photoacoustic CT technology, we try to use unfocused transducers, then use reconstruction algorithm to do the software focusing, essentially, right, to get an image. Here, we're going to use physics to do the image reconstruction or to do the focusing. All you have to do is to use a acoustically focused ultrasound transducer for that purpose. Let's assume there's an optically absorbing target in a piece of tissue we want to image. We fire a laser pulse onto the tissue, let photons scatter. Right? If you want to image deep, you can't really stop that very well. Right? But here, any photons, scattered or not, will generate a photoacoustic wave. Now we receive the photoacoustic wave, use a focused ultrasound transducer, we get a time trace like this. And you can see there's going to be a spike corresponding to this target. You can imagine if you have a second target somewhere deeper, you're going to have a later arriving spike. Right? Since we know the speed of sound pretty well in soft tissue, we can convert a time of arrival into depth. And with a single laser shot, you get a depth resolved image. And the time of arrival gives you depth resolution. And the transverse resolution comes from the acoustic focusing. Right? If you have unfocused transducer, you won't get it. Right? Now, of course, the transverse dimension is 2-dimensional, so you get 3D resolution directly by using this technique. Now, a laser shot gives you a 1D image. If you scan across the tissue, you get a 2D image. We call that B scan, where the 1D image is called A scan. If you raster scan on the tissue surface, you get a 3D image. This is the first 3D photoacoustic microscope. We start from a laser. We actually use a tunable laser because we can target chromophores of different colors. You route the laser beam through an optical fiber. You see the solid laser beam coming out of the fiber. that's converted into a hollow cone beam using this conical lens or axial lens. This key component is shown in this close-up, and the hollow cone beam is refocused down into the tissue. On the tissue surface, we have this donut beam where the core is dark, just to minimize the surface interference signals. And this focused transducer aims at the illumination zone for your photoacoustic detection. So this scanning head is raster scanning this water tray. Through this membrane window, we can transmit light and sound. So the tissue to be imaged is placed below the membrane. This was one of the first images acquired using this device. This is a photograph of a melanoma. With the naked eye, you can see a little bump, but you don't see the depth of the melanoma. You don't see the surrounding blood vessel network. And using photoacoustic tomography at 2 different laser wavelengths, we can see both the melanoma and the surrounding blood vessel network with very high resolution. Most melanoma has increased in melanin concentration. Melanin is a great endogenous contrast. We just target melanin absorption for photoacoustic tomography here. Now, of course, in blood vessels, we use hemoglobin as our endogenous contrast agent. For human imaging, it's ready. So we image our own palm here, and you can see the blood vessel network very well. And this is a B-scan image, so the vertical axis is depth, and you can identify some of the standard skin structures. If you were to use X-ray imaging to image blood vessels, you have to inject contrast agents, like iodine, because there's really not enough soft tissue contrast in X-ray imaging. Using hemoglobin as the intrinsic contrast, we don't have to inject anything else. It's already there in the body. Photoacoustic tomography works very well with nanotechnology. And we work with the inventor of nano cages, a colleague in my own department, biomedical engineering department at WashU. He was able to make the nano cages smart enough to target MSH receptors, melanocyte stimulating hormone receptors on melanoma cells, which are hallmarks of melanoma. By using the targeted version of nano cages, the contrast of our image was enhanced by 3-fold in comparison to the non-targeted nano cages. And this can be extremely powerful, not just for imaging purposes, but also for monitoring purposes. My collaborator's lab is also interested in drug release, controlled drug release, through the nano cages, because these cages are hollow. You can load the nano cages with drug, and they actually wrap around the nano cages with a polymer. When you heat up the polymer a few degrees, the polymer will shrink. You open up the pores on the nano cages to allow drug release. And when you cool down, the polymers will reseal the pores. So you can come back and do repetitive treatment. And photoacoustic tomography can be used to monitor the entire process. You identify where to treat to begin with, then you can monitor it. We can also miniaturize our technology, our device, to be compatible with endoscopy. So this is the first photoacoustic endoscope. And the key technical challenge is to combine light and sound somehow in a single tiny device. And we use optical fiber to deliver light into tissue, and we use a ultrasonic transducer at a reasonably high frequency, and but drill a hole in the middle for light delivery. And we use a single surface for both light and sound reflection. So the photoacoustic wave will come back and reflected by this surface toward the ultrasound transducer. Now this whole chamber has to be liquid filled because ultrasound propagation does not like air. And we use a micromotor to drive this scanning mirror. The micromotor does not like liquid. So we separate these 2 chambers and transfer the torque using this pair of magnets. So this mirror is being rotated, as you can see here from this system. Excuse me. So we did an in vivo study in a rabbit esophagus. As we pull back the device, you can see different cross-sectional images. You can see the peristaltic motion in this rabbit esophagus as well. So one of the key advantages of this device is the penetration capability. You see this little mark depth right here. It's about 7 millimeters. All standard optical endoscopy can penetrate up to about 1 millimeter. And there are lesions beyond 1 millimeter in depth, which cannot be captured right now. So by using photoacoustic tomography, we can potentially overcome that problem. Photoacoustic microscopy also comes in optical resolution, where we're back within 1 millimeter penetration capability. In fact, this particular device penetrates about 1.2 millimeters in the skin. So within this 1 millimeter range, you can focus light. So photons are not fully scattered, fully diffused yet. There are still some photons that are ballistic or quasi-ballistic, meaning travel relatively straight toward the target region. So what we do here is to combine the optic axis with the ultrasonic axis. The key component is this device, light-sound combiner, made of 2 prisms with a gap in between. The gap is filled with a liquid. So the optical refractive index is well matched along the optical axis, but at the interface, the acoustic impedance is mismatched, which means the ultrasound signal will be reflected toward this ultrasound transducer. So we're able to combine the optical and acoustic axes in a single system. When you fire a laser pulse, you get a 1D image along the depth direction, because the time of arrival of the acoustic signal will give you the depth resolution. However, the optical focusing will give you the transverse resolution. So you can focus light quite tightly in this case. In this particular version, we demonstrated about 2.6 micron transverse resolution. As we know, the smallest blood vessels, namely capillaries, have a diameter of 5 to 7 microns. So at 2.6 microns, you can see the smallest blood vessels, namely capillaries. And we use this technique to do a study to monitor the angiogenesis process. Right. My collaborator, Dr. Arbai, used to sacrifice animals at different time points to get the same data set, because his imaging procedure was invasive. You had to sacrifice the animal, then look at the tissue under microscope. Here, using a non-invasive technique, we can monitor the same animal over a period of 60 days. Okay. And so you avoid this inter-subject variability in statistics that can save a lot of animals by using this method. And you can see increasing vessel density and as well as increasing vessel tortuosity. And this is a 3D rendering of the data set. The recent version, in fact, the previous image was acquired using the 5 micron system. The current version is 2.6 micron transverse resolution. And this is the entire vasculature in a mouse ear captured using the system non-invasively. You have to zoom into a small area to look at the details. We can see a single capillary bed. We can see single capillaries. You can even see dots lining up this single capillary. These are single red blood cells. Okay. So now we can also build a submicron system, right, that allows you to see single red blood cells, even the donut shape of the single red blood cell. As we know, RBCs are biconcave in structure, and we can see that quite well. Also, for the first time, we're able to see intussusceptive angiogenesis. You see this vessel here, there's a hole in the middle. Unlike sprouting angiogenesis, here we see a process where a single vessel is being drilled in the middle. You're splitting a single vessel into two. By drilling in the middle, then somehow seal them together. So all previous studies were done using electron microscopy. That means you have to sacrifice the animal and cut out the tissue and do it in ex vivo. But here we monitor the process in vivo. We're also interested in studying the brain at high resolution. We worked with a neurologist at Washington University. He can tolerate the removal of the scalp, but not the skull. The minute you remove the skull in a small animal, you cause artifacts. So here we keep intact skull. We can see all the detailed blood vessel structures. If you want to use a dye to stain some of the structures in the skull, methylene blue would be a good choice. And this is methylene blue absorption at 650 nanometers. That's the peak absorption wavelength for the dye. So we're interested in using this for Alzheimer's disease study. Human applications. And you can see the capillary loops in our finger cuticle. Because oxy and deoxyhemoglobin molecules have different colors, by tuning the laser wavelength, we can quantify the concentrations of both forms of hemoglobin, from which we can quantify the oxygen saturation of hemoglobin. That's a very important physiological parameter. And if we zoom into a single capillary loop, you can see on one side it's highly saturated, on the other side it's much lower. And what it says is most of the oxygen is unloaded at the tip of the capillary. This is an entirely new phenomenon, never observed before. We can continue the path to shrink the resolution, and we can improve the NA until we get the diffraction limited at the highest possible NA. For this particular one, we demonstrated 220 nanometer transverse resolution. We can also tune the laser wavelength to target some other absorbers. And in this case, we used UV light to target DNA and RNA absorption directly. And so without labeling the tissue, we can image the cell nuclei directly. Right? So this is essentially label-free in vivo histology, because we can do this in vivo now. And this same piece of tissue was later processed using standard histology, meaning you have to stain the tissue, right, using HE stain. And this is the stained version. You can see how well we can acquire a label-free image of the cell nuclei, just as you would in standard histology. And this can potentially find broad applications for tumor margin detection. Because standard histology, this is what they do. They look at a cell nuclei distribution to figure out if there's any residual cancer. When you operate on a patient, you want to remove all the cancer cells. You don't want to leave residuals there. So instead of waiting for a pathologist to come back and tell you if you clear the margin, we can do it in the OR in real time. There's photoacoustic Doppler effect we can use to image blood flow. And so here I showed 3 images. Not only can we image the total concentration of blood, the oxygen saturation of blood, but also the blood flow velocity. In fact, we can image the cross sections as well of the blood vessels. Photoacoustic tomography is the only technique that allows you to image all 5 intrinsic parameters, which can be used to quantify the metabolic rate of oxygen. So the metabolic rate of oxygen is an important parameter in physiology as well. As we know, what is wrong with cancer? Cancer has a problem with metabolism. So if we can image metabolism early, we can potentially provide early detection of cancer. So using this technique, we found something striking recently. So this is an early stage glioblastoma tumor in a mouse. We can see the increased metabolic rate of oxygen very early on. But unlike commonly believed, there is hyperoxia as opposed to hypoxia in the tumor. Right? This is because there is much increased blood flow rate, which overcompensates for the high demand in oxygen consumption. So a quick discussion followed by summary. We're exploring light but we're also interested in microwaves and radio frequency waves for even deeper penetration. Right? So we tested this concept using a 3 gigahertz microwave source that allows you to image the breast. We imaged a few mastectomy specimens, and this cancer, breast cancer, showed up as a 5:1 contrast. This one is about 3:1. All of these are intrinsic contrast. So this can be interesting as well. Instead of using a laser pulse to generate photoacoustic signal, use a microwave or radio frequency pulse instead. And this is very recent work, and we found a method to focus light into biological tissue. This method is called time-reversed ultrasound encoded optical focusing, or true optical focusing in short. You've heard of guide stars used in astronomy, which has been used to offset the disturbance due to the atmosphere to the wavefront. But in biological tissue, we don't have a guide star to begin with. You can implant a fluorophore, but you can only implant it at one spot, right? To generate the image, you have to correct at every spot. So instead of implant a fluorophore, we use ultrasound. We just focus ultrasound beam into biological tissue. The ultrasound beam is going to tag photons. When light travels through the ultrasound focus, it'll have a frequency shift. It's like you change the color of the light by a tiny bit. And outside the tissue, we can separate the tagged photons from the background untagged photons. We only record information from the tagged photons, then time reverse the process back to the ultrasound focus. So this is what this right movie is showing. In the interest of time, I'll now talk about the left movie, which is a baseline. So this method allows you to focus to anywhere inside a highly scattered piece of tissue. This can be extremely powerful because it has potential applications in everything you do using light, including imaging, sensing, manipulation, and therapy. You know, you've heard of photodynamic therapy. How do you focus to the lesion you want to treat? You've heard of optogenetics. How do you deal with activities deep inside tissue? Right now, we use optical fibers. We insert it invasively. But if you use true optic focusing, you can go much deeper. So in summary, photoacoustic tomography has been achieved by optical excitation and ultrasonic detection. The diffusion limit has been broken. Super depths up to 7 centimeters have been reached. Single capillaries, even single cells, be resolved in vivo. 220 nanometer resolution has been demonstrated. Multi-scale imaging is possible by scaling the depth and resolution. Intrinsically, photoacoustic detection is background-free, meaning when there's no absorption, there's no signal. From the engineering perspective, that's the most desirable situation. In fact, photoacoustic tomography has the high sensitivity among all imaging modalities to optical absorption. Either non-fluorescent or fluorescent pigments can be detected. Even count-on fluorescence, but if there's a partial fluorescence quantum yield, it doesn't hurt us that much. And if you depend on fluorescence, there's only a subset of molecules among all molecules that you can detect. But all molecules will be absorbing. It's a matter of finding the right wavelength. There are multiple chromophores you can resolve spectrally. And from the intrinsic contrast, we can provide you functional imaging of physiological parameters. By introducing targeted contrast agents, we can provide molecular imaging. Reporter genes can be imaged as well. Doppler effect allows us to image blood flow. Frame rates can be potentially very high. So far, we demonstrated about 50 hertz online rate, 249 hertz offline rate. But the fundamental limit is much higher than that. There are no speck artifacts, very different from pure ultrasound imaging or OCT. Only non-laser radiation is used, so it's very safe. The systems are relatively low cost. However, we do need contact measurement because ultrasound propagation does not go through air-tissue interface very well. So we typically use gel or liquid. Cavities and very thick bones can potentially attenuate our ultrasound signal, but this may not be such a fundamental issue because we're finding ways to overcome this problem. If you're interested, there's a tutorial type of chapter in our book, Diametric Optics. There's also a much detailed edited book on this topic. Many experts in this field have contributed to this book. Thank you very much.
Thank you, Mr. Wong, for a very beautiful summary of this very exciting area. Any questions?
The 7 centimeters, does that mean that the light is actually penetrating 7 centimeters?
Yes.
And then, so how much light are you actually using?
So we stick to the ANSI limit, 20 millijoules per centimeter squared, right? Usually a few centimeters in diameter. So we can use tens of millijoules oftentimes.
Is there any kind of reference?
ANSI limit. There's it's published. There's you know ANSI, right?
Yeah, I just mean, just, is there any intuitive reference to think about?
Reference for our paper, or reference for this work, or reference
Just
for the
intuition of how bright it is.
oh for that for the fluids limit, or for I'm
Just
trying
how
to,
much light are you using, just intuitively? Because I can't imagine joules. What's a pointer laser? What's a laser?
okay. If you walk outside in the sun, right? That's roughly about 100 milliwatts per centimeter squared, right? So we use 20 millijoules if we run that at 10 hertz. So it's about 200 millijoules per centimeter squared. So it's twice, roughly twice of a 4 days sun exposure at that time. This ANC limit is very conservative because the damage threshold is at least 10 times that level. More or less like, over 100 milliwatts per centimeter squared. The worst scenario, like really dark skin. Or, dark skin has lower damage threshold because of the element absorption. Does that make sense?
Questions?
I think this can replace the radiology that we're currently using all over the place for medical imaging.
All right, we tell our colleagues we don't replace anyone. We're looking for certainly many applications, possibly. We're starting from the breast because it's relatively acoustically homogeneous. The thickness is not terribly demanding, right? Because a compressed breast has a median thickness of maybe 45 centimeters. We're not compressed sideways. We can compress any direction, or even uncompressed might be able to be accommodated. We're also interested in brain imaging. We want to start from neonates, where the fontanelles are open, the skulls are relatively thin, and the bone is relatively soft. So we usually targets to begin with. But I'm certainly very interested in adult brains as well. And the GI tract is obvious direction as well. So we're starting with Barrett's esophagus monitoring. If we have the device built. We're also interested in endometrial imaging. Colon would be an obvious target. So there are many possibilities. But overall, I'm not so sure we're going to replace all the standard modalities because all modalities have a place. Like you can argue MRI can replace X-ray CT, but not quite true. Because X-ray CT still has the speed that MRI cannot reach. Right? Even though MRI has non-negative. Right, so I'm a strong believer most modalities will have a place and will coexist.
The use of fluorescent dyes seems somewhat paradoxical. I think that you would want to use pigments that are non-fluorescent, so that it would all be thermal dissipation rather than optical.
Right. So, correct. So, but even a reasonably good fluorescent dye, oftentimes like ICG, has a fluorescence quantum yield of roughly 10 to 15%. So most of the energy still goes into the thermal channel.
And the absorption is very specific.
Yeah, you have absorption spectral signatures that you can use. So in fact, we actually concurrently image fluorescence and absorption using photoacoustics. So you can get both modalities to work together. Sometimes you can find reasons to do that as well. You're exactly right. From the physics perspective, you just need absorption. But a little bit of fluorescence loss it doesn't really hurt.
I had a quick question on your assumptions when you're doing the tomography reconstruction, that the acoustic signatures from any volumetric point is omnidirectional. But clearly because of occlusions and scattering and other opacities, that's probably not true. So how do you deal with high quality reconstruction?
So if you have very strong acoustic heterogeneities, and then acoustic scattering or reflection will become issue. So in that spinal image I showed, where you get a full body spinal image, the bone actually is the problem. So the spinal cord is going to reflect sound. And if we just do standard reconstruction, we get artifacts all over the place. And what we did was to only keep the first half of the data. So you can see your signal will arrive as far as the full diameter. But we keep it up to the radius, half the diameter. So only the first half of the data is used for reconstruction. The reflected signal oftentimes arrives later. And so we truncate that part of the problem. You're exactly right. Until we have a better model to take that reflection into account, and that's our current solution. But the optical heterogeneity is not an issue. So it's just acoustic heterogeneity. For example, in the breast, in the breast we don't have that issue. And in the human adult brain, the skull thickness will be a big issue. And so we're still looking for good solutions for that problem.